Hi there. Thanks for joining us yet again on another episode of Space Nuts. This is a Q&A edition. My name is Andrew Dunkley, your host. Good to have your company. What we're going to tackle today is questions about bright nebulae. And that's a question that comes from Dan, and it's probably not where you're thinking in terms of what he might be asking. You probably don't know what the heck he's asking at all, but we'll tell you. Also, this one came through Instagram. Renee has sent us an article about light traveling in two directions. What's that about? Rusty has a three-body problem, and Martin wants to talk about brown dwarf stars, and he also wants to tell us a poem. It's always dangerous, but we're going to do it here on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
He's back again for more. His name is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Glad to be here.
Good to have you here.
Yeah.
Isn't it funny how we always seem to wear the same shirts 2 episodes running?
I don't know how that works. Yeah.
Just no idea. Very strange phenomenon. Now, we might as well get straight into it and tackle our first question, which comes from Dan.
Hi, gentlemen. This is Dan from the Gold Coast. I just wanted to know, with some of the bright, kind of more colorful nebula, like the Carina, Helix, Cat's-Eye, that kind of stuff, would being inside there, would you be able to actually see all those colors, or like, is it kind of like once you're in when you're up high in the fog and that, it's a little less noticeable? Is that what it's like in there, or do we not really know what it would be like? Thanks for taking my question. Love the show, and thanks for keeping me company on my deliveries for work. Cheers, guys. Bye.
Nice one. Thank you, Dan. Glad we can keep you company. Bright nebulae. When they're photographed, they look extraordinary. Some of the colors are amazing. But when you photograph Earth, it's the same thing. But when you're down here, you go, oh. So is it the same if you go into a nebulae or a nebula?
I think you would see the colors, actually. So you've got to imagine, first of all, you're not just sitting in the middle of a nebula. You're probably in orbit around a star on a imagine us on a planet that's around a star in one of those nebulae. Now, the issue is this may not happen because we know that those nebulae are associated with star-forming regions. So they're young stars that are in them. And some of those young stars might be too young to have mature planets with intelligent life on it. But if there was intelligent life on the star or the planet of a star in a glowing nebula, I think you'd see the color. I think you would see a background, and it would probably predominantly be pink because that's the color of excited hydrogen. What's exciting it is the ultraviolet light being given off by a nearby star. That ultraviolet light will be lethal for us anyway. So
I knew there'd be a fall of some kind.
Yeah, you might not see it for very long. But yes, I think if your eye was in there, you would see the colors.
That's interesting because
maybe more subtly than what we see in some of the photographs, but
yeah. A lot of those photographs have to be enhanced and to bring out the detail, I suppose. And those photographs have improved over time with technology, because some of the early photographs of like the Horsehead Nebula were a bit fuzzy, but if you look at the latest crop of them, they are certainly high definition.
Yeah, that's right. That's largely a result of bigger telescopes. I mean, it was my colleague and friend David Merlin, who lives not very far from here at Bayview. He was the person who first put colors into images of the stars using predominantly photographs, and there were photographs from the Anglo-Australian telescope and the UK Schmidt telescope. That's the one I came to Australia to work on. So and I was going to say, when you talked about color enhancement, things like that, he took extraordinary pains to make sure that the colors he was presenting were what your unaided eye would see if you had a much bigger telescope. In fact, he was obsessive about it, the color balance, to the extent that he would get really upset if he went to give a talk about these things, and the video projector that was being used was not up to scratch. He'd be tinkering with the adjustments, trying to fix it before the talk. So his images were a representation. Now, you're quite right that, when those images came out in the 1970s and 80s, they were mind-blowing. Nobody had ever seen anything like them. But we now have images from much bigger telescopes. We've got images from space telescopes, which by definition don't have the blurring effect of the atmosphere in front of them. They're seeing perfect images, unfettered by the atmosphere. And also from the ground, we're seeing from much bigger telescopes now, twice as big, and that also affects the definition. So yes, the current crop of images which we're getting from the Webb telescope, the Very Large Telescope, the Gemini telescopes, all of those, they are stunning. You're absolutely right.
Okay, question without notice. Which nebula is the brightest and most colourful?
I think there are two very bright ones. Probably the one that everybody on Earth can see, because it's right on the celestial equator, is the Orion Nebula. And that's visible clearly with the naked eye. Big gas cloud in the constellation of Orion, right just below. It's actually the handle of Orion's sword. That's where it is, or the handle of the saucepan, depending on which way up you're looking at it.
Yeah.
And the Lagoon Nebula is very bright as well. That's one of the Southern Hemisphere nebulas in the Southern Milky Way.
Okay, really good. Dan, if you would like to look at some of David Malan's amazing photography, just do a web search for his name, because they'll pop up. And he was a real pioneer.
Absolutely. Yeah, very much so. And he was highly regarded. He won many awards, including the sort of Nobel Prize of Imaging, which is the Leonard Nelson Award. He became very famous because of his images being so widely distributed. They were sought after for record album covers and magazine covers and books. And many very eminent astronomers today, and just two to name, in fact, probably name three: Dame Jocelyn Bell Burnell, Brian Cox, Brian Schmidt, credit David's photography for some of their interest. Actually, Jocelyn was already well into astronomy, but she's always had high praise for David's photography.
Yeah, I'm sure David would not be a fan of the cameras on an iPhone, because I read an article today just to learn a bit more about how to use the camera on my phone. And I found out that because of the artificial intelligence that's built into them, they do tend to not produce what is really seen. I mean, to an unaided eye, it looks like the photo that you took, but the way the artificial intelligence works, it takes a very educated guess as to what you're photographing and fills in the blanks. And I thought, that is weird. I mean, that's not how a camera should work. But what's interesting about it is that they question whether or not some of the photos taken by iPhones would actually be legitimate evidence in court.
Yeah.
Even though the image is obviously what you took a photo of.
Yes.
It's not an image of the photo. It's not the photo.
It's not a genuine representation of what the thing looked like. Yes.
Yeah, it's quite incredible. Thanks, Dan. Good question, and keep on trucking or vanning or whatever it is you do.
3, 2, 1.
Space nuts.
Now, our next question sort of came about by accident. I was just sort of milling around on the interwebs over the weekend, and I saw a little one, and the little ones that are on your smart devices. And I thought, oh gosh, someone sent us a message through the Space Nut Instagram page, which I very rarely look at, and it was Renee. Hi, Renee. And she said, I found this article. Maybe you guys could have a talk about it. That was the question. The article was about how physicists have uncovered evidence of two arrows of time emerging from the quantum realm. Now, this is getting into tricky science, Fred, but light is always an intriguing subject. So I thought we might have a talk about this one.
Yeah, it's, it's time we're talking about, not light. It's actually time flowing.
Oh, sorry, I said light. Time.
Yeah. And so, the conventional view is that there's an arrow of time that just goes one way. And it's linked with the second law of thermodynamics, which is all about entropy, which is the randomness or disorder that you find in a system. And all of that stuff gets mixed up. But conventional physics has believed that the arrow of time only goes one way. But this new paper, it's suggesting that in the quantum world, there might be another one that you can basically, follow time going in a different direction. It's going the other way. In other words, going from future to past. Work that one out.
I'm struggling to understand the concept. I know there's been a lot of science fiction about time travel, and I know there's been experimentation. That, like, as you said in the past, traveling through time would require more energy than there is in the universe.
Yeah, that's right.
So
that's the time warp. That's right. That's the warping a bit.
But experiments into time have shown that movement does disrupt the space-time continuum.
Oh, that's right. Time's flexible. We know that because of relativity tells us that, either by things traveling very fast or putting it in a gravitational field that bends time. But this is something different. The arrows of time. I've got the University of Surrey, which is where this work has been done. I've got their press release in front of me, and I'm just going to read from that because it's a very succinct way of expressing it. A new study reveals that opposing arrows of time can theoretically emerge from certain quantum systems. And there's a quote from Dr. Andrea Rocco, who's an associate professor in physics and mathematical biology at the University of Surrey. And it says, the quote is, "One way to explain this is when you look at a process like spilt milk spreading across a table, it's clear that time is moving forward. But if you want to play that in reverse, like a movie, you'd immediately know something was wrong. It would be hard to believe milk could just gather back into a glass. However, there are processes, such as the motion of a pendulum, that look just as believable in reverse. The puzzle is that at the most fundamental level, the laws of physics resemble the pendulum. They do not account for irreversible processes. Our findings suggest that while our common experience tells us that time only moves one way, we are just unaware that the opposite direction would have been equally possible."
Oh, gosh. I mean, that's just hard to wrap your head around, really.
It gets harder when you look at actually what they've done. And it is all in the subatomic world. You're talking about quantum systems and the way they interact with their environment. It's very interesting stuff, but it is quite, it's quite dense. I know I am. So there's another sentence, if I may, from the University of Surrey press release. The system behaved this is the something they're working on a theoretical, in a theoretical quantum environment. The system behaved the same way whether time moved forwards or backwards. And that's saying, it's like a pendulum, which you don't notice the difference either way, time moving either way. The discovery provided a mathematical foundation for the idea that time-reversed symmetry still holds in open quantum systems, suggesting that time's arrow may not be as fixed as we experience it.
Wow. Of course, there's a lot of work going on in the quantum realm.
Yes, there is, yeah.
Because they're trying to crack the secrets of developing quantum computing. And if they do that, it's just going to change. It's just going to change everything.
That's right.
The day may come where we have quantum computers in the home. I don't think it'll be soon, but computers in households are so common now. Whereas when I was a kid, the Casio calculator was a new thing, and when you were a kid, the abacus would have been.
Yeah, the best thing I had was my slide rule. Yeah. I've got a soft spot for slide rules. Actually, I just found one in a antique shop just a few days ago, which is a lovely little 9-inch slide rule.
Look at that.
In its own box. It's been the treasured possession of some engineer, probably.
Yeah.
It's a very nice little purchase.
Good on you. Wow.
Yeah.
I don't know what we're going to pick up in those little...
No, that's right. You don't.
Not much more we can say about this one, but thank you, Renee, for sort of bringing it to our attention. If you'd like to read up on the arrows of time, not light, time, surrey.ac.uk is the site. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, let's move on to our next question with one of our regular collaborators, and that is Rusty.
G'day, Fred and Andrew and Fred. It's Rusty in Donnybrook. Been a while. At this time of the year, who knows where you two are, or I'm sitting at home. I hope this finds you, and I hope it finds you well. Been looking at the three-body problem of the Earth, Moon and Sun in terms of Lagrange points in the Sun-Moon system. The L1 and L2 points in that Sun-Moon system lie about 29,000 kilometres from the centre of the Moon, or about 27,000 kilometres from the Moon's surface. If the Moon was orbiting the Sun without the Earth, they'd be pretty stable, but the Moon goes around the Earth at about with an orbital speed of about 1 kilometre a second, and the two of them travel around the Sun at about 30 kilometres per second. So the impact on L2, for example, in the Sun-Moon system would be fairly slight. And the impact of the Earth-Moon L1 and L2 positions, which are about 4,000 kilometres further out from the Moon, would be probably the biggest effect there. They would have the distorting effect. The question is, the Sun-Moon L2 point, perpetually shaded by the body of the Moon, would that not be a great place to have a habitat? It would shelter, it'd be healing there from solar weather, and to build it lighter, say 50% lighter probably, wouldn't that be a great place to have a habitat? Anyway, I'd love to hear your comments on that one. And I've really been enjoying your show. I haven't had a chance to say anything. Cheers.
Thanks, Rusty. Nice to hear from you. Yes, we're in the country together at the same time for a change, but it's only for a short while. I think I'm the next to make a sojourn overseas. Rusty's three-body problem talks about the Earth, Moon, and Sun Lagrange points. Bottom line is the Sun-Moon Lagrange point a good place for a habitat?
And the answer is no.
Oh, gee, I thought it would go the other way.
No, and Rusty's already put his finger on it. They don't really exist, those Lagrange points, because they're completely unstable. The fact that you've got the Earth right next door, if it was just the Sun and the Moon, yes, that would all be great, all would work. But you've got this massive object, the Earth, 80 times the mass of the Moon, 380,000 kilometers away, and it basically just disrupts the Sun-Moon Lagrange points. So it's got really no stability worth speaking of, and so it wouldn't be a good place to try and put a spacecraft.
So you do, in fact, have with the sun, the Earth, and the Moon a three-body problem.
You do, yes, that's right. It's a three-body problem, and the two absolutely significant bodies in that are the Earth and the Sun. The Moon, it almost doesn't register. It's possible to calculate where those Lagrange points will be, but they're so unstable that there's no point in trying to put something there.
You'd constantly be having to move around to stay in the right place, I imagine.
Yeah, that's right. You burn all your fuel up.
Unless you've got a Winnebago. I mean,
yeah.
That would work. They've made their way into space. Although there are Lagrange points that we've found very advantageous, and we've got a couple of observatories get around those points.
That's right. That's the Sun-Earth Lagrange points where you're right. There's observatories at both L1 and L2. L1's between the Sun and the Earth. L2 is on the opposite side of the Earth from the Sun, 1.5 million kilometers away. And that's where the Webb telescope is, for example, the Gaia spacecraft.
But again, you're not staying still. They still have to maneuver to stay.
Yes, that's right.
Place. And it's like a spiral movement from what I can tell.
Yeah, it's they're kind of in orbit around the stable point, but it's not that stable. If you get tipped off one way, you could run away. So you do need to keep burning fuel to keep it in the right place. It's called station keeping, and I think that's the everyday job of some of these spacecraft drivers, if I can call them that.
Yeah. Okay. So ultimately, with an object like James Webb, the fuel's going to run out.
Yes, that's right. And that's actually what will limit the life of the Webb telescope, the fuel that will keep it in the right place. I think they've got more than they expected to have when they launched it. They thought they had a 10-year life, but I think they're now talking about more like 20 years. So that's really good.
Wonderful. Although in the 20-year lifespan of James Webb, the technology is probably going to jump even more.
Yes, that's right.
There'll be telescopes that will be far more superior, which is what happened to Hubble, basically.
Yep.
Although it's still doing a fantastic job.
It is, yeah.
So Rusty's answer is no go, unfortunately. Although I'm sure the day will come where they'll put a habitat out there somewhere and or a space station of some kind. And I think Earth orbit would be the logical way to go at this point, wouldn't you say?
Yes. Sorry, do you mean around the moon? Moon orbit. Yeah.
Moon orbit.
Yeah, that's right. Well, that part of the Artemis deal is to have the Gateway spacecraft, which is exactly that. It's a mini space station in orbit around the moon. I don't know whether it's ever going to happen, but that's certainly in the planning.
Yeah, you never know. All right, thanks, Rusty. As always, deep thought type questions coming from you. Speaking of deep thought, our next and final question comes from Martin.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres. Recording this in Potomac, Maryland, USA, although by the time you broadcast it, I may well have joined you down under, because I do not wish to live under the possible reign of the Orange Nero. So I have a question about the brown dwarf stars that you blokes were discussing. See how I said blokes? Mm-hmm. Could there be, in theory, an Earth-sized moon of such a brown dwarf star circling it, orbiting it in a possible Goldilocks zone? And would it then be possible for this world to support Earth-like life as we know it? If the answer be yes, what would the brown dwarf star look like in its sky? And I have written a poem about this possibility, inspired by Dr. Fred Watson and Mr. Robbie Burns. All that I know of a brown dwarf star is it can glow, but not very far. Now a dart of bronze, now a dart of tan. Behold its long fronds, the color of bran. My star that dartles the bronze and the tan. No, it's not like a turd. It had fun and world, busy fusing away like the stars all above it. What if circling it is a Goldilocks world? What a strange, lovely thought. I really do love it. And you can send, thank you. You can send the royalties for that to me either in Potomac if the Orange Nero has not returned, or maybe in Dubbo if he has. Berman Gorvine, over and out.
Oh, that is priceless. Absolutely priceless, Martin. Thank you. I know it's taken me a little while to get to that one because apparently the Orange Nero is alive and kicking.
So you might look out for Martin on the streets of Dubbo.
Yes. I'll keep an eye out for him. Yeah. And you're more than welcome, Martin. Anytime. I love that poem. That was brilliant. Very, very good. So the Earth-sized moon orbiting a brown dwarf star in the Goldilocks zone, could it sustain life as we know it?
Well, it wouldn't be as we know it, because the peak energy output of a brown dwarf star is well into the infrared. They've got a low surface temperature. I'm just trying to think whether they even have a Goldilocks zone. I guess they must do, but it might be very close to the surface of the brown dwarf, because they glow just by, by their internal low-level nuclear reactions. So just let's think about, so if I imagine, thinking about warm bodies like us, we radiate at 10 microns in the infrared. That's the wavelength that we emit in the infrared because of our natural heat. And I don't think brown dwarfs are that far away. They're probably a bit warmer than that. They're probably more, rather warmer than whatever it is, 37 degrees Celsius that we have to be. Would there be a Goldilocks zone? I need to check on that. Whether you... okay, good. Yeah.
Apparently, you can calculate it. So it does have a Goldilocks zone, although it does. There's one article I'm reading that says that the first 10 million years of a brown dwarf might have a temperature close to 3,000 Kelvin, a reasonable habitable zone to go with.
It would have, yes.
Yeah. But look, I haven't got anything in terms of...
Yeah, that's a young brown dwarf. So old brown dwarfs, you probably forget it.
Yeah.
The habitable zone is on the surface. They do have weathered brown dwarf stars.
Do they?
Yeah. One of my colleagues, Chris Tinney, before he became an expert on extrasolar planets, used to study brown dwarfs, and I think one of his papers was about the weather on brown dwarfs.
Okay. Well, there's a graph there that gives me an indicator of a habitable zone around a brown dwarf, but I don't understand it. It's got all these 10 to the 5th, 10 to the 6th numbers.
Yeah, right. I better have a look at that.
Yeah. But I suppose the answer is yes, there's a habitable zone under certain circumstances in the early life of a brown dwarf. But, how do you predict what kind of life could be sustained?
Certainly, we're very tuned to the wavelengths emitted by the sun, where sort of all our vision is predicated around visible light peaking in the green region of the spectrum. I guess a creature could evolve with infrared sensitive eyes. That's not out of the question. It's not impossible.
Well,
but
rattlesnakes have.
What do?
Rattlesnakes.
Yeah, yes, there you go. And so, but would it be life as we know it? Well, it might be rattlesnakes, yeah.
Yeah, could be. Yeah. It's hard to know. But and as we've talked about it in the past about how different stars would create different kinds of habitat, like the vegetation would be very different if let's say you had a planet around a very big bright blue star. Everything would be different. As life as we know it would not look like that. If you went into a forest on a planet around a star like that, it would be a completely different kettle of leaves.
Would.
Yeah,
not leaves.
All the colours would be different. All the variations would be different. And because life would have to adapt to a completely different light pattern and heat pattern and everything else, radiation, etc. So, it's a bit of an unknown, Martin, as to what kind of life would exist on a moon-sized planet orbiting a brown dwarf star. But if it was possible, it would not be life as we know it. I think that was the basis of your question. So I think we can give you a no on that one, but not a no on life of some other kind. I think.
Not as we know it.
Not as we know it. James T. Kirk would probably say that too. It's life, Jim, but not as we know it. No, that wasn't Jim. That was Dr. Thing. That? No.
Bones.
Bones. You can say that. Not as we know it. Thanks, Martin. Love the poem. You ought to publish that. That was hilarious. And we are done. Don't forget to send your questions in to us via our website because we love to get them and we're always looking for more. And you can do that at spacenuts.io and just click on that little AMA thing at the top, which is where you send your questions in audio or text format. And don't forget to tell us who you are and where you're from and have a look around while you're there. Visit the Space Nuts shop. It's always fun. Plenty of things to grab hold of. If somebody special is having a birthday soon, you might want to pick up a little doodad for them. Who knows? And thanks as always, Fred. It's been a great pleasure.
Good to talk, Andrew, and look forward to doing it again.
Very good. We'll see you soon. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio because he's always helpful, except today when he couldn't be with us because he was out babysitting his brown dwarf. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com. This has been another quality podcast production from bytes.com.